Our next speaker is Ahmed Zaher, who is going to tell us something about control flow.
All right. Hi, everyone. Thanks for coming. Today, I'll be presenting our paper, Exploiting the Sparseness of Control Flow and Call Graphs for Efficient and On-Demand Algebraic Program Analysis. This is a joint work with my colleagues at the Hong Kong University of Science and Technology. So the main point of this paper is to provide efficient algorithms. So first, I'll give some context on which problem we're trying to solve efficiently, and then I'll highlight some of the main ideas in our algorithms, and then I'll give experiments and conclusion. So let's start. Suppose that you have a program like this that you wish to verify. And by verify here, I mean that you want to compute a value that summarizes the behavior of this program. Well, one step towards that is to abstract away the syntax by means of a control flow graph, where each node roughly corresponds to a line of code. For example, this line 2, corresponds to this node. And the edges of this graph, they correspond to the flow of control. So here we have an assignment. It goes directly to the next line 3. But here we have a while. We can have possible branching based on whether or not the while condition is true or not. If it's true, we go to line 4. If it's false, we go to line 7. And then we consider a universe of summaries, A, and the values of that universe, they would correspond to summaries of executions in different parts in my program. And then we define a semantic function that maps edges in that graph to a value that summarizes the effect of taking that edge during execution. And we further extend that by defining an algebra over our summaries that has operators for choice, sequencing, and iteration. And using these two things, we can summarize the entirety of a program that has sequencing and has while loops and has if and else. But we're not interested in just summarizing a whole program. We're interested in something more general. So in particular, we're interested in this collection of values. For each pair of program lines, I and j, we're interested in xij, which should stand for a summary of all paths starting at I and ending at j. These values are what we want to compute. Here's the algebraic approach to compute such values. So suppose we want to compute xij. We first generate a regular expression that is over the alphabet. Its alphabet is the edges of my control flow graph, and we want that regular expression to recognize exactly the path from I to j. For example, here, if we consider nodes 2 and 7 in this graph, this is a regular expression recognizing all paths from 2 to 7. The next step, to actually get the value of xij, we simply interpret this regular expression using our semantic function and algebra. So we simply replace every edge with its semantic meaning, and we take every operator in the regular expression and replace it with the corresponding operator in my algebra. And what are the applications to this? There are a wide variety of problems in numerical invariant generation and predicate abstraction that can be modeled and solved within this algebraic framework. And we consider an on-demand setting where we have a large stream of queries. Each of them is a pair of program points. And for a query ij, it asks simply for the value xij. And our goal is to answer these queries fast. Why do we care about this on-demand setting? Well, one example is that you can think that we have a large code base and we have many developers debugging this code base, and each of them are sending queries of this form. They're asking to summarize paths from point I to point j. So more precisely, here's our problem. There's an offline input, which is our program, and an algebra and a semantic function, which correspond to the analysis task we wish to perform. And there's an online input, which is a series of queries. Each of them is a pair of program points. And for each query, we want to compute a regular expression recognizing paths from the query's endpoints, and we want to interpret it in the input algebra. And this should explain this part of the title, On-Demand Algebraic Program Analysis. We are referring to this problem here. And what we do in our paper is that we give algorithms to solve it efficiently. So our algorithms, they have a pre-processing phase where we pre-compute some of the queries that have certain special form, and when we later receive a query online, we express it as a combination of the pre-computed queries. And our algorithms are efficient in the sense that both the pre-processing and the query time are fast. And if we first consider the intraprocedural case, where this program, it corresponds to only a single function. In this case, we exploit the sparsity of control flow graph. We note that control flow graphs, they are not arbitrarily complex, that they have some nice structures that we can use. And for the interprocedural case, well, we don't handle it directly, but we do give an algorithm if we suppose that each function is summarized and given at the input. And for this case, to maintain efficiency, we additionally exploit the sparsity of call graphs associated with the program. And this is this part of the title. We exploit the sparseness of control flow and call graphs, and we do that to achieve efficient on-demand algebraic program analysis. So I hope now that the title of our paper makes more sense to you. Okay, let's get into some of the ideas in our algorithms. Let's consider first the intraprocedural case, where we have the same problem, but now we know that our program is represented by a control flow graph of a single function. Apparently, this is a very standard graph problem, which is that of computing path expressions. And that problem was already figured out by Tarjan back in the 70s. So if we suppose that n is roughly the number of lines in my program, and that each of these algebra operation, it has cost k, then Tarjan's algorithm, it works on reducible flow graphs, which capture almost all control flow graphs. So it is applicable to our problem. And the algorithm, it computes all queries for a fixed starting point in nearly linear time, which is very nice. But this algorithm doesn't work because it doesn't suit our on-demand setting. If we have many queries with many different starting points, then naively repeating this algorithm would give us a quadratic runtime. And in our paper, we present two algorithms. The first one, it exploits the nesting depth of the program. Unfortunately, I won't be able to talk about it, so you can see the paper. And the second algorithm, it exploits Treewidth, and this one I will talk more about. Okay, so what is Treewidth? Treewidth is a parameter that measures for a graph how similar it is to a tree. So if a graph has low treewidth, it is more tree-like, and therefore it admits this structure. It admits a tree decomposition of small bags. What do I mean by that? This is a graph on the left. On the right is a tree decomposition of that graph. It is simply a tree, where each node in that tree, we call it a bag. It corresponds to a subset of nodes in the original graph. And when the graph has low tree width, these bags are small, and this has the nice property that it allows us to successively break this bigger graph on the left into smaller graphs. And we are guaranteed that these smaller graphs are connected or glued together using small cuts. So this enables a kind of a divide and conquer algorithm where we solve the problem on the subgraph, and to measure the answers for the original graph, we exploit the fact that we have small cuts, so we can afford some brute force over these cuts and obtain the answer for the overall graph. Okay, how does Treewidth relate to our problem at all? Well, Thurup showed in '98 that control flow graphs have constant treewidth. And an implication of that is that we can assume an extra input, which is a tree decomposition of the control flow graph, and that this tree decomposition has small bags. Now let's try to solve this problem. We are getting queries online, we want to answer them. One naive idea would be to pre-compute all possible queries. And of course, this doesn't work because there are quadratically many queries, and that will take too much time and space. Our approach is to only pre-compute special queries that have certain nice form, such that when we get an online query, we can express it in terms of a combination of the special queries that we already pre-computed. And we want the number of special queries to be significantly less than quadratic. Otherwise, it doesn't differ from the naive approach. And of course, we want the total runtime to pre-compute all of the special queries to be small. So to do that, we will exploit our extra input. So suppose that this is our control flow graph, and this is its tree decomposition. This tree decomposition, it has some properties that give us the following lemma. And it says the following: if you consider two nodes, U and V, in the original graph, like those two here, then you can identify in the tree decomposition, you can identify two bags, BU and BV, like those shown here in bold, such that the path connecting BU to BV, it is a path consisting of bags, and each of these bags forms a cut that separates U from V in the original graph. So this sounds complicated, so let's see an example. If we pick this bag on the path from BU to BV, it would correspond to this cut, and because it's a cut, if we remove it from the graph, U and V are separated. If we pick this other bag, we remove it, we get the same effect. These two nodes are separated. And this gives us means to break down our query. So if we pick any bag on this blue path, we can break a query from U to V, like this. And so this doesn't only give us a way to break our query, it gives us a choice as to where to break our query. And our idea is to make one canonical choice, which is always the least common ancestor of BU and BV. So in this example, we'd always pick this bag and break our query there. So here's an example. If we pick this bag, a query from 11 to 10, it would be expressed like this. And by this choice, our special queries, we can define it to be all pairs of nodes whose corresponding bags in the tree decomposition are kind of in an ancestor-descendant relationship. And this already gives us an algorithm. In the pre-processing phase, we pre-compute all of these special queries. When we get a query UV, we find the two bags, BU and BV, we find their least common ancestor, and we apply this formula. And by design, we are guaranteed that these things, these answers appearing on the right-hand side, they are special queries, and therefore they are already pre-computed. And then we can compute this whole value. And if we analyze this, we find that the number of special queries is n times the height of the tree decomposition. And if the tree decomposition is too long, then this is bad. We can have quadratically many special queries, which is too much. So we overcome this by defining another decomposition called centroid decomposition. We define it over this tree decomposition. So it has some properties. One of them is that it has height log n. And we, instead of choosing the point where we break our query to be the least common ancestor in this tree decomposition, we choose it to be the least common ancestor in this centroid decomposition. So in this example, we would pick this bag, which corresponds to this bag here, which corresponds to this cut. And now we fix our problem. The number of special queries is n log n. And if you look at the paper, you will see how we pre-compute all of these special queries in n log n times k. That was for the intraprocedural algorithm. How do we handle the interprocedural case? Again, I won't have much time to talk about it, but we simply extend our algorithm by considering another graph, which is the call graph of the program, and we capture the sparsity of that call graph using another graph parameter, which is Treedepth. And we actually did some experiments. We performed some standard data flow analyses that can be formulated within the IFDS framework. So we did reachability, uninitialized variable, and null pointer analysis. And in this case, each algebra element is the graph representation of the IFDS framework. And we tested this on programs from the Kabo benchmarks. And here's a comparison of our algorithm versus using Tarjan's algorithm. We basically run Tarjan's algorithm for every query, and our algorithms indicate by squares. Tarjan is by triangles. And this is time in log scale, and clearly we're doing faster. We did another experiment where we analyzed Boolean programs, and in this case, each algebra element was a state transformer that's represented by a binary decision diagram, and we use Boolean programs that are generated from Windows drivers while doing abstract interpretation. Again, here's a comparison. To conclude, we gave fast algorithms for on-demand algebraic program analysis. For the intraprocedural case, we exploited sparseness of control flow graphs, and we captured it by Treewidth. In the interprocedural case, we looked at another graph, the call graph, and we captured its sparsity by Treedepth. And we gave experiments showing that our algorithm is faster than using Tajan's algorithm for every query. And that's all for my talk. Thank you very much.
Thank you, Ahmed. Any questions?
Thank you for your talk. There is some clarification question. Your algorithm is n.log(n.k). Does it independent with the Treewidth?
No, we assume that the Treewidth is constant. But the actual dependency on Treewidth is, I think, in our algorithm, it's cubic.
Okay, thank you. And I'm also curious about if this algorithm can be generalized to maybe answer data log queries or.
I'm not familiar with that, so I don't know.
Thank you.
Thanks.
Thanks for the great talk. I have a question about the on-demand part, the query. What's the complexity of the single query?
Oh, the complexity of a single query. Let's go back. Yeah, we simply apply this formula, and it reduces to a number of queries that is proportional to the number of nodes in this bag, which is bounded by the Treewidth. So it's Treewidth times a cost of an algebra operation.
Oh, so it's not exponential with respect to Treewidth.
No, it's Treewidth times k, where k is the cost of an algebra operation.
Okay, thank you.
Thank you, Ahmed.